Welcome to the next lecture in Math 1316 at Dallas College Trigonometry. We're looking at Chapter 3.3, where we've been looking at radian measure and the unit circle. We're going to look at the unit circle and circular functions today. So circular functions, the value of these functions, determining a number given, and function values as lengths of line segments. We're not going to spend a lot of time at the end. This is a higher level trigonometry concept. So the first thing we want to talk about is a unit circle. And so what a unit circle is a circle that has its center at the origin, and then the radius is just one unit. And you can see that here from the origin to the x-axis. You can see that 0.10, and then you can see that continuing around. Now what this does is it allows us to think of just the x and the y values as cosine and sine, because remember that cosine was x over y. You know, when we look at the opposite over the SOHCAHTOA, the adjacent over the radius, that would be x over the radius, but the radius is 1, and so now it's x. So it allows us to simplify the values of the circular functions, okay? With the radius being 1, when we divide by the radius of 1, we get the value itself. So on the unit circle, the first thing we recognize is that sine is equal to the x value, and cosine is equal to the y value. This will greatly simplify all of our measures around the 2 pi circle, if you will, the 2 pi radians as we go around the circle. What it also does is, of course, we know from Pythagorean Theorem that x squared plus y squared equals hypotenuse squared. In this case, it was, you know, the side squared plus the other side squared equals the radius squared. But if the radius is 1, 1 squared is 1. So for the unit circle, we get x squared plus y squared equals 1. So we call these circular functions all the trig functions when we look for their values on the unit circle. So again, here we have sine is equal to y, cosine is equal to x, and then by using all the ratios that we know, for example, tangent is sine over cosine, we get y over x, and then we can see all the reciprocal functions here as well. So if we go around the unit circle and point out the known angles that we've been doing with the triangles, the right angle triangles, the 30, 60, 90, the 45, 45, 90, then we can see that these xy values in quadrant 1 for 30, 45, 60, and 90 give us the same values in every single quadrant for the reference angles. In quadrant 2, we start from the x-axis and we go up to 30, 45, 60. Of course, when we go from the x angle and get the reference angle of 30, the actual angle is 150. So all that changes here, notice the values are the same, but the polarity changes of x's and y depending upon the quadrant that you're in. So the unit circle is symmetric with respect to the x-axis, the y-axis, and the origin. So if a point AB lies on the unit circle, so do A negative B, negative AB, and negative A negative B. And this is just what I was saying, that if you remember all the values of the x and y coordinates for the first quadrant, then the only thing that's changing in quadrant 2, 3, and 4 for the reference angles is the polarity. And that's easy enough to see depending upon where on the axes you are. For example, quadrant 2 and 3 are negative x values because they're, you know, that's where they're on the left side of the graph. Quadrant 3 and 4 are negative y values because they're on the bottom part of the graph. So for a point on the unit circle, its reference arc is the shortest arc from the point itself to the nearest point on the x-axis. This is nothing new. This is what we called reference angles from the very beginning. I'm not going to go through this. This again is looking at, you can see the values of cosine and sine are all numerically the same, but the polarity is changing. So if you want to take a little time and look at this, it's just talking about the different quadrants and how you find the reference angle 180 minus the angle, or pi minus pi over 3, etc. I'm not going to go through this again because this is the same thing that we did for the regular reference angles. Again, I think I mentioned this as well. So we know from the unit circle that x squared plus y squared equals 1. This is the Pythagorean theorem, because that we can make a right triangle with any point x, y in the x and y axis, and then the hypotenuse is the radius of that circle. But notice, since cosine equals x and sine equals y, that we can convert this Pythagorean theorem or identity into a trigonometry Pythagorean identity, which is cosine squared plus sine squared equals 1. So the domains of the circular functions are the same as they are in any other trigonometry functions. Sine and cosine are defined everywhere on the graph from negative infinity to infinity. Tangent and secant are undefined at odd values, odd multiples of pi over 2. So 90, 270, or here pi over 2, 3 pi over 2. And that, what's in the parentheses here at 2n plus 1, is just saying that this is an odd multiple. So if n is 0, then we get 1. If n is 1, we get 3. And so again, we're looking at really the y-axis, the 90 degree and the 270, where tangent and secant are undefined. For cotangent and cosecant, this is the straight line, so any value of pi, so 180, 360, etc., anywhere along that y-axis. Cotangent and cosecant are undefined, so they can be any values but those. When we're evaluating a circular function, the values of real numbers are obtained in the same manner as trig function values of angles measured in radians. This applies both to finding exact values such as reference angle analysis, that we already talked about that, and to calculator approximations. However, as we've been learning for a lot of these, that the calculators must be in radian mode when we're working with circular function values. Example 1, find the exact circular function values of sine, cosine, and tangent, all of 3 pi over 2. 3 pi over 2, this is the equivalent of 270 degrees. It is the downward facing y-axis. The xy point is 0, negative 1. We know that sine is the y value, cosine is the x value, and tangent is y over x. So here we can easily see that sine is going to be y value, or negative 1, cosine is going to be 0, and tangent is undefined because it's y over x, or sine over cosine, and we're dividing by 0. Here we have the unit circle with all of the values filled in. A lot of students will memorize the unit circle. It's not that hard really if you, again, memorize one quadrant. And these are actually the measures that we built from the angles in chapter 1 or 2 from the 90-degree triangles, 30, 60, 90, or 45, 45, 90, etc. So once you remember these first 3 angles and I guess the 90 degree, the quadrantals, then you just change the polarity. Okay, so here if we go to 7 pi over 4, this is getting really close to almost all the way around. We can see it here, and we can see that the cosine again is the x value, so it would be square root of 2 over 2. The sine value is the y value, which is negative square root of 2. Okay, x and y. Cosine is x, sine is y. Careful, because intuitively, if you've been working with trig for a while, we tend to put sine first, which makes us think it's the x, but it's not. Use the figure and the definition of the tangent to find the exact value of tangent. Remember, tangent is sine over cosine, so y over x. Here we're going a negative direction, so we start on the x-axis and go clockwise. Negative 5 pi over 3 is almost all the way around, so 6 pi over 3 would be all the way around. So 5 pi over 3 is 1 pi over 3 less. So if we start at 1, 0 and work our way around, negative 5 pi over 3 is the same as pi over 3. Again, we divide y divided by x, sine over cosine, and we just get the square root of 3. Square root of 3 over 2 divided by 1/2 is the same as multiplying by 2, and so we just get, here we go. We just get the square root of 3. Use reference angles and the radian to degree conversion to find the exact value of cosine 2 pi over 3. So 2 pi over 3 is in the second quadrant, right? Because we're not at 1 full pi, we're 2/3 of pi. So we're 2/3 of the way around to the straight angle. So this corresponds to an angle of 120 degrees, 2/3 of 180. In the standard position, 120 degrees lies in quadrant 2 with a reference angle of 60. Remember, we measure from the 180 or the y-axis up to that angle. We always measure reference angles from the x-axis up or down to the smaller acute angle to the angle given. So the cosine of 2 pi over 3 equals the cosine of 120, which again, remember this is the reference angle 60, but since it's in quadrant 2, x is negative in quadrant 2, so we get the negative cosine of 60, which equals negative 1/2. Here we're just going to plug these into our calculator and find values. Go ahead and try these. You can hit pause just to make sure that you're doing them correctly. And again, we can do cotangent as well. These are good ones for you to see. How do we do that? So if we're trying to find the cotangent value on our calculator, it's 1 divided by the tangent of that same thing. Remember, this is an inverse function. The same with secant. Secant is the inverse of cosine, so we do 1 over cosine of that function. A common error in using a calculator in degree mode when radian mode should be used. This is very common. Remember, if you're finding a circular function value of a real number, the calculator has to be in radian mode. We've seen this